Okay, so here we are trying to find relative extrema, relative max, or relative means of the mean values of the function. And remember that for this, we have two different tests. First derivative test says that to find relative extrema, you need first to find uh, f prime. And so let uh, C be a critical point of f at which f is continuous. Let me just put this condition. You can have a little bit different conditions there, but we need continuity at least. Then f at C is a relative max for f if this happens that f prime changes sign. Oh, let me just first write the general thing, relative extrema. So fc is relative extremum value for the function if the f prime, if the sign of f prime before and after c are different. Meaning what? If this is c and this is f prime, if before c, for the values less than c, the function is f prime is negative, then positive, that means that the function itself, so this is me saying a little bit more details, means that f is decreasing first, then increasing. And that shows that if c is a relative mean value. If the other way around happens, so before c, well, this can be just close. It doesn't need to be up to negative infinity, just close to c. So if before that, f prime, before that is positive, then negative, that means that f itself is going to be first increasing, then decreasing. And that would give us the relative max value. So using the first derivative, you can fix where which one of critical points are relative max, relative mean, or which one is not any of these ones. Okay, so let's start with this. So f first, find critical points. Well, we first look at f. F is tan inverse of a function. Tan inverse is differentiable everywhere, first of all. It is defined on the whole real line. So it means that tan inverse is nice. Tan inverse of e to the power x minus x is differentiable everywhere, and it is defined everywhere. So f is defined and is differentiable on the whole real line. Why is that important? Because critical points are the points at which Either f prime does not exist, f prime is not defined, or it is defined and it's equal to 0. By knowing that it is differentiable on the whole real line, we now know that the critical points only can happen where the derivative is equal to 0. We don't need to be worried about the points at which f prime is not defined. Okay, so let's see what is f of x. F of x is tan inverse of e to the power x minus x. Remember, when you want to differentiate tan inverse of u, the derivative you make is u prime in the numerator. This is the chain rule version of derivative of tan inverse. 1 plus u squared. Okay, so here then f prime x is going to be e to the power x minus x prime over 1 plus e to the power x minus x squared. And that will give me e to the power x minus 1. Derivative of e to the power x is e to the power x minus 1. 1 plus e to the power x minus x squared. If we set this guy to be equal to 0, you have quotient of two functions. If the whole thing is equal to 0, it means that the numerator must be equal to 0. Okay, you have an exponential equation, you can solve it, and x is going to be equal to ln of 1, or let me just write 0. Okay, so we found out that there is only one critical point there, x equal to 0. Now, not all critical points are relative max or relative mean. We may have critical points which is neither relative max nor relative mean. But what does say which one of these guys are relative max mean? We just said first derivative test is one way, the second derivative test is another one. So what we need to know is, let's use first derivative test. Meaning that, well, let's see how the derivative of the function before 0 and after 0 changes the sign. One interesting fact here to see that the denominator 1 plus e to the power x minus x squared. You see, something squared is always non-negative. Any number you square it, you will get non-negative numbers. So this part is going to be bigger than equal to 0. And then you add to that 1. So that means that the denominator is always 0. Denominator is not going to change the sign of f prime. The only place the only part that changed the sign is the numerator. And look at e to the power, that's not a good one. And look at e to the power x graph. This is e to the power x, and this is y equals to 1. So we know that on this interval here, let me just go with the red. On this part, 1 is bigger than e to the power x. That means that e to the power x minus 1 is going to be 0. So here, this will be 0. How about here? Okay, here I can see easily that e to the power x, the graph of e to the power x is above graph of y equal to 1. So e to the power x is going to be bigger than 1. So e to the power x minus 1 is going to be positive. So this will be positive. You can evaluate the function at some values. For example, you can put here, you can put ln of, I don't know, 3 for this one, for some values. And here you put, I don't know, minus ln of 3. And that will tell you what are the values, well, what are the sign of the function over there. Okay, so we defined the sign table for f prime. Now it's time to use the first derivative test. It says that, okay, the last part I am adding just to show you what does that mean. This is decreasing, this is increasing, and as you can see, we are having relative, so f has a relative mean at x equal to 0. So that is where the relative mean occurs. But what is the relative mean value of the function? So f at 0 is a relative mean value of f. And what is that? F at 0 is tan inverse of e to the power 0 minus 0, e to the power x minus x, and that is tan inverse of 1. And we know that tan inverse of 1 is pi over 4. So it means that relative mean value of the function at pi, relative mean value of the function is pi over 4. And it occurs at x equal to 0. So this was an example to cover first derivative test.